On the 13th of June, 2025, an emergency began at Marina Pinnacle. Above you, fire is moving upward through the upper portion of a 67-story tower. Inside, 3,820 residents are moving down. Outside, an entire emergency network is moving in. This single building holds 764 apartments. Authorities confirmed that every reported resident reached safety. But if everyone survived, what exactly did this massive mobilization expose? A skyscraper is not only a building, it is a neighborhood standing vertically. We must start by acknowledging the absolute scale of that survival. Authorities reported no initial injuries among the thousands who escaped. Firefighters successfully controlled the incident over a demanding 6-hour operation. Medical teams provided immediate support on the pavement. Temporary accommodation was successfully coordinated between authorities and the developer for those who were displaced. Nearby transport operations were adjusted to secure the area and support emergency access. But this incredible outcome should not mask the mechanical reality of what happened inside the walls. Thousands survived because multiple independent layers of technology and infrastructure had to operate perfectly before the event crossed its final safety margin. Reporting 0 casualties describes the final outcome of the night. It does not describe every physical system that had to activate to achieve that specific result. So what actually happens before those internal systems activate? What turns an ordinary local ignition source into a tower-scale emergency in previous Dubai fires? A successful evacuation does not mean the building was not severely tested. A successful outcome can still reveal a massive infrastructure dependency. To understand how a fire travels, we have to look at previous verified incidents. In 2012, Tamwheel Tower experienced a major fire that exposed the mechanics of vertical escalation. Dubai police concluded that the event was probably initiated by a discarded cigarette. That cigarette landed in an exterior passageway. It ignited a pile of rubbish that included paper, tape, and wood. The fire then reached the exterior cladding of the structure. From there, it traveled rapidly upward along the outside of the building. Burning facade material began falling from above, affecting additional balconies and creating secondary ignition points on lower levels. The fire reached the roof of the tower in approximately 10 minutes. One single ember, one massive tower, 10 minutes of travel time. The ignition was small. The route it took was not. This incident forces us to separate two entirely different questions when investigating a high-rise emergency. What started the fire? And what allowed the fire to become so large? We must clearly separate the original ignition source from the subsequent escalation pathway. The cigarette initiated the event and explains the first flame. The building supplied the route and explains the scale. During ordinary use, a facade system performs a vital but passive role. It separates the interior floors from the external climate, managing heat and preventing moisture intrusion. It might consist of panels, cores, insulation, cavities, and window assemblies. But under the wrong conditions, that same exterior envelope can change its function entirely. It can become a vertical route connecting every floor. Performance during an emergency depends heavily on material composition, cavity barriers, and the integrity of the fire stopping. It depends on how the geometry of the building interacts with the wind and the surrounding air currents. When a fire takes hold of the exterior, it moves upward while dropping burning material downward. It effectively bypasses the solid concrete floors that normally prevent internal fire spread between apartments. Before we look at the internal warning systems, you need to make a judgment. When a fire begins outside a high-rise, which system has the least margin for error? Detection, containment, or evacuation? Keep that choice in mind as the fire continues to move. The facade is not only a surface. Under the wrong conditions, it can become a vertical road. I initially assumed that a functioning alarm system would immediately see the entire incident. I thought the building would instantly know when and where the danger started. but a detector responds only to the exact environment it is designed to monitor. In the Tamwheel Tower investigation, interior heat and smoke detectors activated much later in the timeline. They were delayed because the fire began entirely outside the occupied interior space. If you chose detection in our earlier question, you now have the physical evidence to support your position. A delayed warning cuts directly into the critical time needed for containment and human escape. Initial awareness often relies on external callers, security cameras, or residents simply noticing smoke outside their windows. Internal alarms eventually trigger when smoke penetrates the monitored interior spaces or when extreme heat transfers through the glass. But even after that digital warning finally arrives, the physical reality of the building remains absolute. Every single person inside must still move through the escape route running opposite to the fire. A detection system can work exactly as designed while the earliest fire remains completely outside its view. You receive the warning and make the immediate decision to leave. You open your apartment door, enter the corridor, and leave your home behind. You reach the protected staircase and begin the long, demanding descent. You watch the floor numbers repeating endlessly as you move downward with hundreds of other occupants. You have limited information and no clear idea where the fire is actually located. The physical distance to the street feels immense, and the physical fatigue grows with every flight of stairs. This is the central tension of a vertical evacuation. The fire does not need to enter every single apartment to cause a catastrophe. It only needs to compromise or threaten the specific route that everyone depends on to survive. If the fire breaches the staircase pressurization or bypasses the heavy fire doors, the entire evacuation sequence is threatened. Let us return briefly to those three private choices. Detection identifies the danger. Containment delays the danger. Evacuation moves people away from the danger. These critical systems are sequential, not interchangeable, and they must all function perfectly under immense pressure. A high-rise must meticulously protect the path moving opposite to the flames. We cannot talk about repeating fires without examining the history of the torch. This is a 79-story residential tower located in Dubai Marina. It experienced significant, highly publicized fires in both 2015 and 2017. During the 2017 event, authorities were forced to evacuate hundreds of occupants in the middle of the night. Verified footage showed fire moving rapidly along the exterior and burning debris falling to the streets below. It is crucial to remember the context of this specific building. When the second fire occurred, the tower was still dealing with repairs, insurance assessments, and recovery from the incident 2 years earlier. I would not treat this repetition as proof that every repair failed or that authorities simply ignored the building. I would treat it as hard evidence that repairing one specific incident and upgrading an entire generation of occupied buildings are two completely different tasks. When you deal with legacy buildings, you face a massive, intricate logistical challenge. You need extensive inspections, repair approvals, facade replacements, and complex insurance negotiations. You have to arrange safe access to occupied apartments without displacing residents permanently. You have to manage enormous costs, assign legal responsibility, and eventually pass rigorous reinspection. A repeated incident turns one building's fire into a broader question about infrastructure age. In 2015, the Address Downtown Hotel caught fire in a highly visible event. Dubai police conducted a thorough investigation and concluded that the cause was an electrical short circuit. The specific fault involved cables connected to an exterior spotlight on a ledge between the 14th and 15th floors. Because the fire began outside occupied interior space, internal alarms did not sound immediately. Smoke simply had not yet entered their monitored area to trigger the sensors. Investigators confirmed that no criminal intent was involved in the incident. This specific event forces us to reject a very common oversimplification. A Dubai tower fire does not automatically equal a cladding fire. Forensic analysis must separate the event into 6 distinct layers. ignition, escalation, detection, evacuation, suppression, and recovery. Cladding or a facade assembly can heavily influence the speed of spread without being the original ignition source. An electrical fault can begin an incident without explaining the entire later pathway of the flames. A fire alarm can activate successfully without containing the fire. A protected staircase can remain fully usable without suppressing the flames above it. One material may explain part of the route. It cannot explain the entire emergency. So let us return to the events at Marina Pinnacle. Thousands of residents have successfully navigated the stairs and reached the pavement. Has the emergency now ended? To understand what happens next, you have to translate those evacuation numbers into actual city functions. 764 apartments and 3,820 residents represent individual homes. They represent heavily used lifts, parking facilities, water distribution, power consumption, communications, and security systems. They involve daily food deliveries, waste removal, medical records, and essential medication. They include pets, work schedules, school runs, and the sudden need for temporary shelter. You reach the pavement, but you have not completed the evacuation. You have simply crossed from the tower's internal infrastructure into the surrounding city's infrastructure. The pavement is not a destination. It is a waiting area where complex urban dependencies are instantly exposed. At this point, is this still a building emergency, or has it become a city emergency? Comment one word: building or city. Keep your answer in mind, because the streets outside the tower will now test it. The final exit door transfers the emergency directly from the tower to the city. While the residents move out, the city must immediately move inward. This external response involves alerts, dispatch, route selection, road access, and precise vehicle positioning. Emergency teams must establish safe command areas and secure a massive, reliable water supply. They must navigate dangerous falling debris zones, clear ambulance access routes, and locate safe firefighter entry points. Extreme height fundamentally changes the logistics of this entire operation. Upper floors far exceed the reach of any ordinary external firefighting ladder. This means the internal systems of the building suddenly become absolutely essential to the responders outside. Internal pumps and vertical fire water pressure matter immensely. Dedicated firefighter lifts and protected internal shafts matter just as much as the trucks on the street. Even the geometry of the surrounding roads affects where emergency vehicles can safely position themselves. If you chose building in our earlier question, you can point to the internal pumps, stairs, and shafts as the critical elements. If you chose city, you can point to the access routes, the responding vehicles, the command structure, and the water logistics. Height changes both the building inside and the district outside. Neither side can effectively manage the crisis without the complete cooperation of the other. You stand on the pavement watching the massive emergency response unfold above you. But the physical challenge you face is no longer just about avoiding heat and smoke in a stairwell. You now need accurate information, medical assessment, drinking water, and a way to charge your phone. You might urgently need daily medication, critical identity documents, or access to the pets you left behind. You have to manage work disruptions, school disruptions, and wait for updates from building management. At Marina Pinnacle, authorities and developers had to coordinate medical and psychological support for the crowds. Nearby transport operations were significantly adjusted to accommodate the ongoing response. Temporary accommodation had to be found and funded for those who simply could not return home. Residents remained entirely displaced while rigorous safety assessments continued inside the structure. A 6-hour firefighting operation can easily produce a much longer, more exhausting period of displacement. The building produced this massive displacement, but the surrounding city had to absorb it. Extinguishment ends the active combustion. It does not automatically restore a home. The smoke may clear from the skyline, but the logistical burden on the urban environment can persist for weeks. When incidents repeat across a skyline, the immediate public response is often to demand new, stricter regulations. But we have to separate two very different engineering and regulatory problems. Writing a new rule for future buildings is actually the easy part of the equation. A future building can simply be designed and approved under the current United Arab Emirates Fire and Life Safety Code. The real, monumental difficulty is the skyline that already exists. Fixing an existing building requires complex structural audits, advanced material testing, and incredibly difficult replacement work. Engineers have to inspect fire doors, meticulously restore hidden fire stopping, test pump pressure, and verify alarm upgrades. Facade replacement on a legacy building is extremely expensive and requires long, complicated insurance negotiations. Most importantly, these older buildings remain fully occupied while the dangerous work is done. Contractors have to arrange safe access, divide ownership responsibilities, and pass strict re-inspections without permanently displacing residents. You cannot simply turn off a skyscraper while you upgrade its critical safety systems. A new code effectively protects the next building. Retrofit must confront the skyline that is already standing. It is a slow, expensive battle against the materials and standards of a previous regulatory era. To bridge the dangerous communication gap between the building and the city, Dubai introduced a system called Hassantuk. It is a real-time life safety monitoring network connecting buildings directly to the Civil Defense Command Center. When a building safety signal triggers, the digital information journey is nearly instant. The command center receives the exact building location, detailed incident parameters, and the most efficient approach routes. Depending on the configuration, it monitors fire alarms, lift systems, gas detection, and the critical status of fire pumps. It can even detect low fire water levels or unexpected electrical interruptions in safety equipment. This means faster awareness, better situational preparation, and improved routing for the nearest response resources. But there is a strict, unbreakable physical limit to this digital layer. A faster signal cannot magically close an open fire door. A digital dashboard cannot restore missing fire stopping inside a wall cavity. A location map cannot create water pressure, and a control center cannot make a blocked escape path usable. If you chose building, these physical systems still support your position. If you chose city, this monitoring network supports yours. But neither side can operate alone. The city may receive information instantly. The building must still survive physically. Let us return to the incredible outcome at Marina Pinnacle. I do not think the successful evacuation of 3,820 people should be dismissed as mere luck. Residents reached safety. Emergency teams managed a highly complex, dangerous environment and controlled a major incident. That coordination matters immensely. But we have to establish a strict, uncompromising engineering limit on how we interpret that success. The outcome alone does not reveal when every single warning actually occurred. It does not tell us which escape routes performed best or how much vital safety margin remained before a critical system failed. It does not confirm which specific system was decisive, which system needs improvement, or whether a different fire location would produce the exact same result. We must carefully distinguish between a successful outcome and a complete engineering diagnosis. We must ask the hard, uncomfortable question: did the building work flawlessly, or did enough of the system work for just long enough? Reporting no casualties is a powerful, welcome result. It is not a complete technical report. A zero casualty figure proves that the worst-case scenario was avoided, but it does not prove that every internal defense held its ground. A skyscraper fire tests a massive, interconnected chain of urban infrastructure. First, it tests ignition source control, housekeeping, and electrical maintenance. Then it challenges the facade assembly, cavity barriers, fire stopping, and compartmentation. It severely tests detection systems, communication networks, sprinklers, and complex smoke control mechanisms. It demands intact protected stairs, reliable firefighter lifts, massive water storage, and consistent pump pressure. It relies heavily on thorough emergency planning, diligent building management, and calm resident behavior. Finally, it forces a massive response from road access networks, fire vehicles, police units, and waiting ambulances. It requires transport management, temporary housing logistics, rigorous post-fire inspection, insurance payouts, retrofitting, and digital monitoring. We are looking at an entire chain designed to prevent, contain, warn, escape, respond, and recover. No single layer replaces the vital function of the others. Dubai's skyscraper fires are not one identical technical failure repeated endlessly across different towers. They are different, highly specific incidents exposing the exact same reality. Vertical living completely converts building safety into urban infrastructure. A skyscraper's most important infrastructure becomes visible when every single layer is needed simultaneously. If one layer fails, the next layer must absorb the impact, and the final layer is always the city itself. We return to the pavement outside the tower. The fire remains far above. The displaced residents are gathered below. Emergency teams continue their methodical movement inward. We began with flames moving up and residents moving down. But the larger, more complex story was the third crucial movement: the city moving in. A skyscraper is not safe simply because one single material does not burn. It is safer when multiple, independent layers continue working flawlessly after another layer has already been challenged. This documentary does not claim that every Dubai tower fire had the same cause, that every facade system is combustible, or that the 2025 Marina Pinnacle fire has officially been attributed to cladding. It uses documented incidents, official investigation findings, published fire safety requirements, and emergency response systems to examine how a local ignition can become a severe test of building and city infrastructure. Technical conclusions may naturally change if newer official investigations are released. In a high-rise fire, what protects more lives, stopping the fire from traveling upward or keeping the escape route downward usable? Choose one and explain why.